Hello, this is Alex, and today I would like to solve an interesting GRE geometry problem. In the figure below, what percent of the larger circle is unshaded if all the circles inside the large circle have the same area and they touch each other as shown? So when I look at this problem, I would like to first define what we're looking for. We're looking for the percent of the larger circle that is unshaded. So we're looking for the percent of the larger circle which is unshaded, right? So I'm going to write that this is equal to the unshaded area divided by the total area of the large circle. I'm going to assume that the large circle has the radius of capital R. So this is a large circle. And all the small circles have a radius of small r. So this is going to be small circle, right? And we can denote this radius here. I'm going to draw it. So this would be the capital R, and there will be a bunch of small r's here, right? And then I would like to further proceed to write out the unshaded area. As we can see, the unshaded area is equal to the area of the large circle, which is capital R, minus the area of all the small circles. How many of those do we have? We have 1, 2, 3, 4, 5, 6, 7. It's actually equal to the area of the large circle minus 7 times the area of the small circle. And I'm going to denote this area with a small r. And all this has to be divided by a times a capital R. So now let's take a look. What do we know about the relationships between the radius of the large circle and the radius of the small circle? As we can see here, the diameter of the large circle actually fits in 3 small circles. So what we could write is that the diameter of the large circle equals 3 times the diameter of the small circle. And since we know that any diameter is simply equal to 2 times the radius, this is true for any circle, we can write that 2 times capital R, which from here is the radius of the large circle, equals 3 times 2 times small r, which is the radius of the small circle. The 2 cancels, and we get the relationship between the large circle, radius of the large circle and the radius of the small circle, and this will help us solve this problem. So we can go back to the original equation, and we can try to write out the areas in terms of the small radius. So we know that the area of the small circle simply equals pi times small r squared. What about the area of the large circle? We know that the area of the large circle equals pi times capital R squared. And now we're going to use the relationship we just found to define it in terms of the small r. So this is pi times 3r squared, which equals pi times, or 9 pi r squared. And now we're going to plug those numbers back into our original equation. So for the capital R, the area of the large circle, we're going to put 9 times pi r squared minus 7 times area of the small circle, which is just pi r squared. And we're going to divide that by the area of the large circle, which is 9 pi r squared. And now, what do we get? We get on the top 2 times pi r squared divided by 9 pi r squared. At this point, we see that pi r squared is on the top and the bottom of our fraction, so we can divide it out. We get 2 over 9, and this equals 0.222. So this will equal to 22.2. Oops, I'm running out of space. So it's 22.2%. One important thing to mention is that we're able to get this percentage without actually knowing what those radiuses are equal to. The important thing is that the relationships between the large circle and the small circle will stay the same regardless of the actual value of the radius, which is really important. I really hope this helps, and if you have any other problems you'd like me to solve, feel free to send them to MathHelpGRE@gmail.com. Thank you.